Hey guys, so this video is going to be about solubility and solutions. So this is really, I think, solutions number 3 video for pre-AP. All right, so solubility. Solubility is the ability to dissolve. Hopefully you remember that. We went over the solubility rules last semester. Here they are. I don't know if this was the same one that we used, but it's the same content. And so just to remind you what happens when sodium phosphate is added to water, we will look over here. It says compounds containing the following ions are mostly soluble. There's no exceptions, and sodium is right here. So that means that this will dissolve, and this is actually what happens. We would do a little activity with this if we were in school, but we're not, and I've looked into it, and it's just too difficult to try to get it in for this online stuff. But basically, this is what you would get, and I'm going to show you. I'll add a short clip of a video to show you how salt and stuff like that is dissolved by water. But basically what's going to happen is this is going to dissociate, and we're going to get 3 sodium ions and 1 phosphate ion because it dissolves. Potassium acetate. So acetates are right here. That thing stays together. It doesn't fall apart. So we would have potassium acetate dissociates into potassium ions and acetate ions, and there's one of each because there's one of these for every one of these. And so we'd have that. And so all you would have to say is what happens when sodium phosphate is added to water is you can say it dissociates into 3 sodium ions and 1 phosphate, or 1 PO4, or whatever you want to say. Okay, and then this one, it dissociates into potassium ions and acetate. Dissociate is just the opposite of associate. Okay, so to associate with something is to get close to it. To dissociate from something is to separate from it. So that's what that means. Now, lead to bromide. Bromide is soluble except when it's with silver, mercury 1, or lead 2, and that's what this is. It's lead 2. So this does not dissociate completely. What it really does is it does this. Okay, so we have 2 bromides there. This means that it's in equilibrium, and we're not going to talk about that specifically, but I do want to say that it dissociates so little that it's mostly this. And so that's why we consider it to be insoluble. And so you could say nothing really happens, or it dissociates a little bit, but not much, or something like that because it's insoluble. Okay, and the solubility rules tell you that. And I don't ask you very many questions about this on your assignment, but I did want to talk about it for a few minutes because I do think that it's really, really, really important, especially in AP. It's important. But for right now, I'm just kind of sticking to the main topics. All right, so what can be done to increase the solubility of salts in solution? So I want you to imagine that you're in your kitchen and you have a big bowl or a glass of water or something like that, and you want to increase the solubility of a salt. So you want to be able to add more salt to the water. What are some things that we could do to get more salt to dissolve? Well, one of it is you could stir it, right? So stirring, the big kid word we use for that is agitation. So we could agitate the solution or stir it, and it would get more to dissolve faster. We could also use a larger surface area. And so if we want to, the easiest thing I can talk about where you would understand what I was saying would probably be something like sugar. So you have granulated sugar, which is like the sugar in your sugar jar or your sugar bowl or whatever, where you grab a spoonful of sugar that's in little bitty pieces, right? Versus a sugar cube. Now, a sugar cube is a clump of sugar that's in the shape of a cube. And if I were to put that in there and then put the same amount of sugar, but in granulated form in the water, which do you think would dissolve faster? Yeah, the granulated sugar would dissolve faster because it has a bigger surface area. Because you can access the little particles more readily. And if you were to add up all the outside pieces of all the particles and compare it to just the outside surface area of the sugar cube, you would have more surface area here. And that's what we mean by bigger surface area. There's more sugar molecules accessible in this one than there is in that one. All right. And then the last thing is temperature. If we make the water hot, we can dissolve more. My son learned that very fast. He's been making Kool-Aid since he was about 5, my youngest son, and he would go in there and he would use warm water out of the tap water to make Kool-Aid, because he figured out he could get more sugar in his stuff, and nobody would notice until somebody else took it. Me and my husband don't really drink Kool-Aid that much, so yeah, it was an interesting thing. All right, so here is this is a solubility curve, and it represents a bunch of different things. So we have sodium nitrate and calcium chloride, lead 2 nitrate. So this line right here represents just sodium nitrate's behavior in water, its ability to dissolve in water at certain temperatures. And so this graph is the solubility of those substances in 100 grams of water. So how many grams of that salt can dissolve in 100 grams of water versus temperature in degrees Celsius. Okay, so as the temperature increases, almost all of these salts increase in their solubility, right? So as the temperature goes up here for potassium chlorate, the amount of potassium chlorate we can put in 100 grams of water is increasing. For potassium chloride, the amount we can put in the water is increasing. So that's what this chart shows. Now, we're going to talk about it more specifically, but I just want to look at, let's do potassium nitrate right here. Okay, so I'm just going to use this for these examples in a minute. All right, so first, let's go over these definitions. It says a saturated solution is when the maximum amount of a solute is dissolved in a given amount of solvent at a particular temperature. So that means you can't dissolve any more. It's full of solute. No more is going to dissolve in it. It's the maximum amount. All right. So what that could look like is you could have a container and it's filled up. And so it's all dissolved in here, right? And it could look like that, where it's completely full of solute, but then you might also have a little bit at the bottom. It's not dissolved in there. That would still be a saturated solution, because since there's stuff at the bottom, that means it couldn't dissolve anymore. And so that would still be considered a saturated solution. Now, as far as the graph goes, if it falls on the line, so we're just going to talk about potassium nitrate. If it falls on the line, that means that solution is saturated. So at 10 degrees Celsius, if we put 20 grams of potassium nitrate in 100 grams of water, so 20 grams of potassium nitrate in 100 grams of water, it would be saturated. All right, so if it falls on the line exactly for that substance at that temperature for 100 grams of water, then it's saturated. An unsaturated solution is when less than the maximum amount of solute is dissolved in a given amount of solvent at a particular temperature. So with this one, you wouldn't be able to tell if it was saturated, unsaturated, or supersaturated if you have this. If there's nothing at the bottom, then you don't know. So it could be a perfectly saturated solution where you don't see any solute sitting at the bottom. A supersaturated solution looks just like it. And an unsaturated solution means you could put more in and it would dissolve. So the only way to know is to add more solute and see if it dissolves. If it dissolves, then it was unsaturated. If it doesn't dissolve, then it was saturated. And we'll talk about what happens when it's supersaturated in just a minute. So potassium nitrate solution, again, at 10 degrees Celsius, if we only have 10 grams in there, if we only have 10 grams of potassium nitrate at 10 degrees Celsius, then it would be unsaturated because it's below the line. So all of the unsaturated solutions would be below its line. Okay, so anywhere below the line for that substance at that temperature would be an unsaturated solution. And then a supersaturated solution also looks just like an unsaturated solution. Okay, it looks the same, but this time you have basically tricked the water molecules into dissolving more than they should. And so what you do is you add your solute, your extra amount of solute, to your water or whatever solvent you're using at a high temperature. And then you start to cool it off. You let it sit and you don't bother it. Now, not everything can supersaturate, but there is some stuff that can. And I had a supersaturated solution sitting on my table before the break. And a couple of you did ask and poke at it and say, what is that? And I said, we'll get to it later. And unfortunately, you might not ever see it. But so anyway, you would basically add more solute. And you would, if everything comes out of solution, so if all of a sudden stuff starts crystallizing, it was supersaturated. And I'll put a link to a video. It'll be a short one, just like the other short 50-second video or something, where you can see a supersaturated solution do this. So for potassium nitrate, again, if you have anything over the line, and it has to be dissolved, then it would be supersaturated. All right. Solubility of gases. So we've talked about solubility of salts, which are just ionic compounds, but solubility of gases are a little bit different because agitation is going to make the gases come out of solution. So think about a 20-ounce bottle of Coke that's at room temperature versus a 20-ounce bottle of Coke that's really cold. If you drink a 20-ounce bottle of Coke at room temperature, it's going to burn your mouth a little bit more. The bubbles will. Versus a cold one isn't gonna burn as bad. And that's because the gases are going to come out easier at higher temperatures, because if we want to get a gas to dissolve into a liquid, we want to slow them down. So you want lower temperature. Okay, so not higher temperature for gases, you want lower temperature because we want to slow them down. And another thing that we do is we use lots of pressure. So if you haven't opened your 20-ounce bottle of Coke yet and you throw it at the ground, it's going to explode because, one, you've agitated the gas molecules and they're all going to come out of the solution really fast. But the second reason is because it's under pressure. And the pressure is there to push the gas down into the liquid. So it's we use high pressure. So low temperature, high pressure. So we want low temperatures and high pressure. So if you look over here to the right, for methane to have a good solubility, as the temperature for methane, as the temperature gets higher, the solubility decreases. Same with oxygen, carbon monoxide, nitrogen, helium. So the temperature increasing causes the solubility to go down. All right, so we're going to use this with a few questions and then it will be finished. So which salt is least soluble in water at 10 degrees Celsius? So I'm going to look here at 10 degrees Celsius and I'm going to look right here. This is the first salt. It's the least soluble here because the solubility is given on the y-axis. And so that would be potassium chlorate. All right, how many grams of potassium chloride can be dissolved in 200 grams of water at 80 degrees Celsius? So first I'm going to find my line for potassium chloride, which is this dark blue one. And at 80 degrees Celsius, I'm going to go up to that line and find out where it hits. And that is like right here. And so that's going to be at about 52 or 53. You might see something different, but that would be in 100 grams of water. And we're using 200 grams of water. So it would be twice as much. It's directly proportional. So that would be about 104 grams. So your eyes might see it a little bit differently, and I'll make sure that I grade your stuff accordingly. As long as you're in ballpark, you're going to be okay. All right, at 40 degrees Celsius, how much KNO3 can be dissolved in 300 grams of water? So at 40 degrees Celsius, we want to look at KNO3, which is the green line, potassium nitrate, and we can dissolve about 63 grams in 100 grams of water. But this is in 300 grams of water. So you can solve it a proportion if you feel like it, or you can just multiply it by 3. And so that would be 189 grams of potassium nitrate. Okay, and one thing I want to remind you, because I don't know if I did it on the thing, is that for every gram of water, it's 1 milliliter. So this could have said 300 milliliters, and it would mean the same thing, just for water. Water has a density of 1 gram per milliliter. So grams and milliliters, the units are interchangeable. All right, which salt shows the least amount of change in solution from 0 to 100? So this is the least amount of change. The slope is the smallest, right? Slope is change. And so that would be sodium chloride. All right, at 30 degrees Celsius, 90 grams of sodium nitrate is dissolved in 100 grams of water. So we have sodium nitrate, and sodium nitrate is all the way up here, this kind of brown line right here. Okay, so at 30 degrees, so 30 degrees Celsius, 90 grams of sodium nitrate. So I'm going to put a point there. And since it's below the line, that means we could still add more, because the line represents saturation point. So that means that this is unsaturated because it's below the line. We could add up to here before the solution gets saturated. All right, a couple more. A saturated solution of potassium chlorate is formed from 100 grams of water. If the saturated solution is cooled from 80 to 50, how many grams of precipitate are formed? So we have a saturated solution of potassium chlorate formed from 100 grams. So where is my potassium chlorate? It's right here. It's done at 80 degrees. So right there. We have 100 grams of water, so this is the exact point. So this would be 37 grams of potassium chlorate. Now we're going to let it cool down. So we still have the same salt in there. It's not like it's going to disappear. But we're going to let it cool down to 50. Now at 50 degrees Celsius, I can only get about, what is that, 17 to dissolve? So that means if the solution does not supersaturate it, which the problem is saying how many grams of precipitate are formed, so I'm guessing it doesn't precipitate, I'm guessing it doesn't supersaturate. That means that 20 grams of KClO3 precipitate, because it can't stay dissolved. All right, and then it says which salt behaves like a gas. So this one behaves like a gas because as we increase the temperature, the solubility decreases. So that would be cerium 3 sulfate. Which salt is most soluble at 10 degrees Celsius? So most soluble would be sodium nitrate. And why does the x-axis only go from 0 to 100? So here's 0, here's 100. Well, it's because below 0, H2O would be solid, and you can't dissolve salt in a solid. And above 0, or above 100, H2O would be a gas. So that's the freezing point and the boiling point of water. And so that's why, because you're not going to be able to dissolve a solid into a solid or a gas with the way that we're looking at it. I think that's it, guys. Let me know if you have any questions.